So trapezoids, shapes like this, don't fall into our nice natural pattern here to like split up in terms of parallelograms and heights in the way that we really like to, but the way that we want to approach this in terms of area is essentially to break it down into better, in a sense, parts. And there are a couple ways we could go about this. We could break this off into a rectangle with two triangles attached to it, in which case we'd have three shapes to deal with, or we could take this and cut it in half, like so, into two triangles that don't necessarily match perfectly in terms of their base widths. That if we did so, we want to get the area there, that's just the amount of space it takes up, that value A would be given by the area of the one triangle plus the area of the other triangle, where they have the same height, that same up and down dotted line, but the bases, A and B, would not necessarily end up being the same value. For a general trapezoid, they shouldn't be the same value. So if we want to get the area, it would end up being 1/2 times the height multiplied by the base lengths added together, A plus B, because we have that common term between each of the areas of the triangles, 1/2 H. But this is a little bit of derivation there. Let's finish off our sections here for our nice rigid polygons in terms of one more example. So for this, we want to find the area of the given trapezoid. To do so, what we want to do is recognize our, let's say, units, as it were. Where again, we could see that we've got a right triangle hanging off of there and another right triangle hanging off of the other side, but actually getting those little lengths in there, not necessarily given, not necessarily obvious. You could do something there that's involving the Pythagorean theorem a couple times, but it's probably not the best use of your time to do that, and you'd end up with something that's probably not very exact. So instead, we're going to talk about what happens here in terms of those bases, 32 and 46 feet, along with the height there of 13 feet. We've got those two triangles stapled together, in a sense, as the other base lengths are both shorter. We would then say that the area in this case is a 1/2 for the fact that we are looking at two different triangles, multiplied by 13 because both of those triangles have height or altitude of 13 feet, then 46 feet plus 32 feet for each of the two base lengths, where this is going to end up leaving us with, skipping a half step there for that arithmetic, 507 square feet. And that's basically all the consideration we're going to make here. Yeah, you could do these sorts of ideas for more complicated, more sided, I guess you could say, shapes, but we're just going to focus on our simple ones here. But next, we're going to talk about something a little different. We're going to look at something a little bit more, how would I want to say this? Curved. We're going to talk about what happens when we're taking these considerations and looking instead at circles, which technically aren't actually polygons. They're their own thing that we're going to see next.